The universe is full of secrets, and some of the most incredible ones are hiding just beyond the reach of visible light. What if I told you that more than 1.5 billion unseen objects, from galaxies and newborn stars to some of the oldest stars in our entire galaxy, are sitting just out of reach of us, cloaked in cosmic dust? That's a little frustrating to think about, isn't it? Until now, that is. Because thanks to the European Southern Observatory's Visible and Infrared Survey Telescope for Astronomy, better known as VISTA, we can finally lift the veil on these hidden wonders. For the first time in human history, we have a pretty comprehensive infrared map of the Milky Way, one that pierces through the obscuring fog of space to reveal an unprecedented view of our galaxy and what lies beyond. I'm Alex McColgan and you're watching Astrum. Join me today as we appreciate how this first of its kind map was made and take a look at some stunning images that reveal previously unknown stars across our galaxy. In September 2024, VISTA published the largest and most detailed infrared survey of the Milky Way ever undertaken. Encompassing a 13-year period from 2010 to 2023 across 140 nights of observation, this project has captured around 200,000 images and generated 500 terabytes of data. That's the same amount of data as it would take to stream a 4K video for nearly 3 years straight. VISTA is part of ESO's Paranal Observatory located in Chile, with its main focus being to map large areas of the sky. Using VISTA's infrared camera, known as VIRCam, the team was able to peer through the dust and gas that permeates our galaxy and uncover some of the Milky Way's most hidden places. Traditional telescopes allow us to view space in visible wavelengths, which range between about 380 to 700 nanometers. But VISTA isn't like traditional telescopes. Instead of relying on visible light alone, VISTA operates at infrared wavelengths between 900 and 1200 nanometers, allowing it to detect otherwise invisible objects like stars obscured by dust and cold brown dwarfs, also known as failed stars, which don't emit enough visible light to be seen with a traditional telescope. To get an idea of the difference between visible and infrared light, take a look at these two images of the Lobster Nebula, or NGC 6357, one taken in visible light and the other with VISTA's telescope. We can see that in the infrared, the dust that obscures our field of view seems to disappear, revealing what look like hundreds of thousands, or maybe even millions, of previously invisible stars. The map was created through VISTA variables in the Via Láctea, or VVV survey, Via Láctea being the Latin name for the Milky Way, and its companion project, the VVV Extended Survey, or VVVX. The data collected from these two companion projects that make up the VISTA Infrared Survey have already led to the publication of more than 300 scientific articles. Unlike other recent space maps, this is one of the most detailed ones ever made. It's the first infrared survey to cover nearly 80% of the Milky Way's luminous mass, and provides the largest infrared catalogue ever made of our galaxy's central region. It allows astronomers to study our galaxy in finer detail than ever before. This survey gives us an accurate 3D view of the inner regions of the Milky Way, which were previously hidden by dust. It covers an area of the sky equivalent to 8,600 full moons, and contains about 10 times more objects than any previously published infrared map from 2012. Our Milky Way consists of a central bulge, a dense, bright, puffed up collection of stars, with a flat disk of 2 spiral arms wrapping from the ends. This image shows the area of our galaxy that was mapped in the survey. The red squares mark the central regions of the galaxy, which were observed by the original survey, and then reobserved again by the extended survey. And the other square colors show areas that were only observed as part of the extended survey. From this image, you can see that these surveys have focused right on the central plane of our galaxy, spanning part of the disk and most of the nuclear bulge. But what has VISTA revealed? Argentinian astrophysicist Dante Minniti, who led the survey project, said, "We've made so many discoveries, we have changed the view of our galaxy forever." And as much as I'd love to talk about all of them in this video, it's probably best I stick to some of the highlights. As part of the survey in 2015, VISTA turned its attention to the star formation region of Messier 20, also known as the Trifid Nebula, which lies about 9,000 light-years from Earth. Viewed in visible light in this image, we can see a beautiful nebula, glowing pink from the emission of ionized hydrogen, and surrounded by a blue haze of scattered light from young, hot stars. The cloud of gas and dust is obscuring the star-filled space behind it. Now, look at this second image taken by VISTA's infrared camera. Peering beyond the clouds reveals a whole swarm of new stars. This image not only allows us to see through the Trifid Nebula, but by chance, it revealed objects on the far side of our galaxy that had never been seen before. To their surprise, astronomers identified 2 faint, reddened objects as Cepheid variable stars. While they appear in the image to be just behind the edge of the Trifid Nebula, in reality they are very distant, about 7 times farther than the nebula that once helped to block them from our view. Cepheid variables are a type of bright star that is unstable. They brighten and fade over a period of a few days or a few months, depending on their brightness. The first variable star we ever identified in modern times was Omicron Ceti, also known as Mira. It had been described as a nova until 1638, when Johannes Halwoods observed it getting brighter and dimmer in a cycle that lasted 11 months. As for this pair of newly discovered stars, they are the only Cepheid variables that we have identified so far in this location, which lies beyond the central bulge on the far side of our galaxy. And they can be really useful too. You can think of them as a kind of cosmic yardstick that can be used up to distances of tens of millions of light years. If you know how long the star's pulsation period from bright to dim is, then you can infer its absolute brightness as well as its age. You can compare absolute brightness to the apparent brightness, that is, the amount of light that reaches Earth, so you have a measure of how distant the star is. With a few reference points like these, we can build up a real picture of the scale of our galaxy and beyond. Looking toward the galactic center, a team of astronomers and data scientists found even more candidate Cepheid stars, 655 in fact. They then sorted these into one of 2 classes, and found that 35 of these 655 stars were classical Cepheids, the younger of the 2. This was really exciting, especially since the galactic bulge was thought to contain mostly elderly stars that are at least 8 billion years old. Recording their pulsation periods, the team revealed that all 35 of these Cepheids were less than 100 million years old, and some of them may be as young as 25 million years old. To put that in context, our own sun is about 4.5 billion years old, so the youngest Cepheid has only been around for 0.6% of our sun's lifespan. The team's exploration of Cepheids culminated in another major discovery. By mapping the 35 classical Cepheids they found, the team was able to trace a completely new feature in the Milky Way, a thin disk of young stars that stretches right across the galactic bulge. Buried behind thick clouds, it had remained unknown in all previous surveys of the region. In revealing this structure, combined with the discovery of older sea feeds as I mentioned earlier, scientists have inferred that there has been continuous star formation along the midplane of the galaxy for the past 100 million years. There might also be even younger sea feeds that we haven't seen yet, as these stars would be so bright that they would be saturated in the VVV survey. The fact that we found this thin disk of young stars within the galactic bulge is incredible. We used to think that the galactic bulge was an ancient feature of our galaxy's past, where exclusively old stars had formed separately from the stellar disk. But this finding reveals that things aren't so black and white, and that the formation of newer stars within the bulge could be a natural progression of our galaxy's evolution. But even more inspiring perhaps is a discovery by the VISTA infrared survey that lies at the ancient heart of our Milky Way galaxy. In 2016, for the first time, a type of ancient star known as RR Lyrae, another variable star, was discovered in the center of the Milky Way galaxy by a team led by astrophysicist Dante Meniti and Rodrigo Contreras Ramos. This type of star is usually found in globular clusters, which tend to orbit the outer regions of the galaxy. A globular cluster is a tightly packed group of stars that contains tens of thousands to millions of stars bound together by gravity. They're also really ancient, containing a stellar population that can be over 10 billion years old. The team found 12 RR Lyrae stars during the VVV survey, which suggests that they might be the remnants of an ancient globular cluster right at the heart of our galaxy. This finding also provides evidence that might help astronomers to decide between the two competing theories of how nuclear bulges form. While some scientists think that the nuclear bulge forms early in the galaxy's evolution, when multiple smaller galaxies violently collide, others say that it forms gradually over time, where gas is funneled inwards to trigger star formation. Finding these ancient stars here suggests that the bulging center of the Milky Way likely grew through the merging of primordial globular clusters, therefore supporting the first theory. So not only does it hint at our own galaxy's beginnings, but it also offers compelling evidence into how these galactic bulges might form in other similar galaxies. Speaking of ancient stars, VISTA was able to find 2 new globular clusters as part of the infrared survey in 2011. In this visible light image, a known globular cluster, UKS-1, can be seen on the right as a hazy red splotch. This cluster had been the dimmest known globular cluster until the new discoveries. Now, compare this same patch of sky, but this time in VISTA's infrared light. Suddenly, we can see what we have been missing. Much more faint than the known UKS-1, we can make out a second globular cluster, this time in the upper left of the image, which has been named VVV-CL001. Another globular cluster, aptly named VVV-CL002, was found soon after, and this small, faint group of stars may be the closest known globular cluster to the center of the Milky Way. Did you know that there were only 158 known globular clusters in the Milky Way before these new ones were found by VISTA? For the survey to identify 2 more of these rare stellar objects is quite a significant accomplishment. Within this central region of the galaxy, it's easy for younger stars and cosmic dust to obscure globular clusters, especially since their age prevents them from shining as brightly. But now that they've been revealed, these features bring exciting possibilities for further study. it could just be an illusion of perspective, but scientists have wondered whether VVV-CL001 is gravitationally bound to UKS1. If this is the case, then they would be the Milky Way's first known binary globular cluster pair. We found binary clusters in other galaxies, like in Centaurus A and the Large Magellanic Cloud, but scientists think it might be when these gravitationally bound clusters collide that we get the most massive globular clusters, like Omega Centauri. So studying a binary cluster right in our own galaxy could produce some amazing insights into this process. It's all speculation at the moment, but it's definitely cool to think about. In addition to globular clusters, the VISTA infrared survey identified a multitude of other types of star clusters. At least 96 new open or galactic clusters have been found, which typically contain fewer, younger stars and are much more common than the globular type. Like the globular clusters, they have been hidden by cosmic dust, but VISTA's 4.1 meter infrared telescope has lifted the curtain to show them in all their glory. Take a look at just a few of these stunning images we now have of these objects. One of these open clusters, VVV-CL003, is much more difficult to make out in images compared to the tightly packed globular clusters. Try and see the density differences in the stars in this section of the image compared to the surrounding regions. It was found by VISTA 15,000 light years beyond the Milky Way center, and also happens to be the first of its kind to be discovered on the far side of the galaxy. The sheer scale of this survey is staggering. Covering a vast region of the sky and mapping more than 1.5 billion objects, this data has already led to fascinating discoveries that are rewriting our understanding of the Milky Way and beyond. And that's just the tip of the iceberg. This survey will serve as a foundation for future telescopes and observations, which will hopefully be able to expand on VISTA's legacy with even higher resolution and sensitivity. We now have the most detailed 3D map that has ever been made of the Milky Way structure and objects, one that unveiled hidden wonders previously beyond our reach, and scientists are already uncovering new galactic features and reshaping our understanding of the galaxy. With the information from this groundbreaking infrared survey, as well as the recent work from ESA's Gaia mission in visible light, it's an exciting time to be an astronomer, and we can expect a flurry of new insights about our own galaxy and the universe as a whole. VISTA's infrared observations have unveiled dozens of hidden star clusters and millions of previously unseen stars. They have revealed new stellar nurseries where stars are born, and they have broadened our understanding of the formation of our Milky Way. Looking at the sky through different wavelengths has brought about a new era of galactic exploration, and I can't wait to see what else astronomers and data scientists are going to uncover thanks to VISTA's 3D map. We do not know the Milky Way galaxy. Yes, even though we are in it. Before you think I'm talking about niche details about stellar formation, how galaxies evolve, or things like that, I'm not. Even some of the basics about the Milky Way are mysteries to us, like how many stars are here? What is its basic shape? Specifically, does its spiral have 2 arms or 4? Although those might seem like simple details, we don't actually know them. Number of stars estimates range from 100 billion to as high as 400 billion, depending on what estimates are being used. Scientists have gone back and forth between 2 or 4 arms over the last 2 decades, and currently we're leaning towards 4. This makes sense. It's naturally harder to look at a thing that you're inside. It's easier to look out your window at the house across the street than it is to look at your own house from that same position. But here's a fun one for you. How many galaxies are in the Milky Way galaxy? According to ESA's Gaia Space Telescope, which just finished its 10-year mission, the answer is not just one. Gaia has been mapping the stars of the Milky Way, performing 3 trillion observations. And now, as it takes its final look at our galaxy, the data is being evaluated. 30,000 stars are moving a little strangely. They are going the wrong way. They are originally not from around here. I'm Alex McColgan and you're watching Astrum. Join me today on a deep dive into Gaia's data to answer exactly how many galaxies did the Milky Way eat. As I already alluded to, looking at our own galaxy is surprisingly hard. I've mentioned before in a previous video how all of the stars, stellar clouds and gas can actually get in the way of what we're trying to look at. This gets particularly bad towards the center of the Milky Way's plane, where the most matter accumulates, creating an area astronomers refer to as the zone of avoidance. Visible light cannot easily penetrate this zone, leading scientists to resort to other mediums like X-rays to scrutinize what lies beyond. To carry on our house analogy from earlier, we are sitting in our bedroom, trying to figure out the layout of the rest of the house, but the walls right in front of us are preventing us from seeing any of the other walls and rooms. Further compounding this is the difficulty in telling how far away a star is from Earth. To make an accurate 3D map of the Milky Way galaxy, you need to know if the stars you can see are dim, small, close ones, or large, bright, distant ones that only look dim and small because of their distance. Not all stars make this easy. While some type of stars, such as Cepheid variable stars, have a predictable enough luminosity that their distance can be calculated if you know a few things about them, not all are quite as accommodating. So, for unpredictable stars, how can you tell how far away they are? The answer is parallax, and that's what Gaia has been using over the last 10 years for its galaxy map. Parallax is the principle that, depending on your point of view, things can appear to be in different places. You can see an example of this right now by holding up your finger in front of your face. Close one eye, then instead close the other. Now alternate quickly between the two. See? Your finger moves quite significantly in relation to its background. The closer an object is, the greater the effect of parallax. Simple trigonometry takes care of the rest, allowing you to calculate how far away an object is. While this effect was very noticeable based on a finger in front of your face, you'll see much less parallax on a tree on the other side of a field, which means it's further from you. The further away something is, the harder it is to use parallax to tell you its distance. Things can get a little imprecise. But how then can we use this method to calculate the distance to a star? The secret is to widen your base viewpoint. Just as the distance between your eyes can influence the effect of parallax on an object, Gaia viewed stars not just once, but multiple times over the course of a decade. In that time, the face of our night sky will have changed, as we can see in time lapses like this one, with an exaggeration of 10,000 times. Rather than using the 6 centimeters between your eyes as the base, every half year we can make the solar system our base instead. Our Earth moves from one side of the Sun to the other, which causes parallax effects to be visible in every star we see. Note how in this animation the stars are taking little looping patterns? That's not really how they're moving, but how we are. That's the effect of our own loops around the Sun. This can help with measuring stars' distance, but there's actually an even larger scale we can use: the proper motion of stars. We can ignore the loops for this one, as an even larger base is coming into play. Rather than just use the motion of our planet on either side of the solar system, we can make use of the fact that our own solar system, along with the other stars in the galaxy, are also moving. So we can use that motion as an even larger base for establishing parallax. The same principle applies. Stars with proper motions against the backdrop of space are closer, while stars with less proper motion are further away. In this way, Gaia has been building a precise 3D map of 2 billion stars in our Milky Way galaxy and beyond over the course of 3 trillion observations. But Gaia has not just been looking at their motion and distance. ESA's mission for this telescope was to study the luminosity, temperature, mass, and chemical composition of these stars too. It houses 2 powerful telescopes that channel light from 2 different directions into a camera with nearly 1 billion pixels, the most precise camera in space. Its radial velocity spectrometer can measure Doppler shift to give us clues about its velocity. It also has photometric instruments to reveal spectral information about each star's properties like composition and temperature. So, although 2 billion stars is only a drop in the ocean of the 100 billion stars thought to inhabit the Milky Way, this still allows us to create an incredibly detailed map of our galaxy over time. And it's that over time bit that allows us to see the Milky Way's eating habits. Since 2013, when Gaia was launched, it has been collecting data which ESA scientists have been processing and releasing in large data packets for the general scientific community to study. The larger the gap in time, the more comprehensive and precise the data. More time equals more parallax. 3 such data releases have taken place so far, in 2016, 2018, and a 2-parter that released a simplified version in 2020 and then the full version in 2022. And scientists have already had the chance to evaluate what Gaia has seen. And as they witness the motions and locations of stars in our galaxy over time, it became possible to model the whole galaxy and even wind it backwards. Take a look at this. It's impossible to photograph our own galaxy, as no camera-equipped spacecraft has traveled out that far. But here is a representation, created using Gaia's data of what it looks like, to an unprecedented degree of accuracy. Note its wobbly edges. These indicated to scientists that the Milky Way crashed into another galaxy in the distant past. Using the second data release, researchers from the Netherlands looked at 7 million stars and found that 30,000 of them were moving strangely. While most stars, including our own, move around the Milky Way in one direction, this odd collection was moving the opposite way. Their color and brightness were also strangely distinct, indicating there was something special about this particular group. The researchers ran the numbers and found that a model that fitted their observations was what would happen if another galaxy collided with our own. The collision must have happened 8 to 11 billion years ago and involved a small dwarf galaxy that the researchers called Gaia Enceladus, or sometimes the Gaia Enceladus sausage. See how its stars, indicated here in red, actually managed to retain a fairly discrete form for a time before eventually spreading out across the Milky Way. This merger may have been an important part of how our Milky Way came to have some of its unique characteristics, such as a bar in the center, something that only 2/3 of spiral galaxies have. The Milky Way didn't go in for a little late-night sausage eating just once though. Another dwarf galaxy, known as Aruya Sequoia Litoi, was also found to have merged with the Milky Way, and perhaps was a binary pairing with Gaia Enceladus. And then, in a later study, another dwarf galaxy's remnants were found. More than one, in fact. According to this study, our Milky Way may have eaten as many as 6 other galaxies. Gaia data reveals this hasn't stopped. The nearby dwarf galaxy Sagittarius has collided with our own 3 times already in the past 4 to 5 billion years, and is set to do so again. This collision may have even been the spark that lit the flame of our very own Sun, which came into being around that same time. Eventually, Sagittarius may well become galaxy number 7 that the Milky Way has consumed, all of its stars being slowly ripped away and brought into our own galaxy. These revelations are just some of the incredible discoveries made possible through the Gaia telescope's data, which is why it is sad that Gaia's time has come to a close. The Gaia telescope maintained its position in the second Lagrange point using judiciously applied cold gas propellant, 12 grams a day. However, that cold gas has finally run out. On the 15th of January, Gaia took its last observation and has begun the process of doing a few last calibrations before finally powering down on the 27th of March 2025. But its story is not over yet. 2 more data packets await release. The first of the 2, Data Release 4, will include 500 terabytes of information and will be released in 2026. It will only cover the first 5.5 years of Gaia's mission, but will do so to an incredible level of detail. Its precise measurements of stars' wobbling motions might even highlight possible locations of exoplanets, and will create the largest catalogue of binary stars to date. It's also worth recognizing that the discoveries Gaia brought us don't end with just prior or ongoing galaxy impacts. It's possible to fast forward the data to model the motion of our local stars millions of years into the future, allowing us to see incredible models like this one. Note how, although the stars near us initially spread out across the Milky Way, they later reconvene due to what is thought to be density waves. Seeing this play out helps explain the spiral arm shape of our galaxy. Gaia data has helped improve our picture of events much closer to home too. Gaia revealed the position and direction of travel of over 150,000 asteroids in our solar system, and thanks to its ability to track those movements over time, Gaia was able to demonstrate that 352 of them probably have moons, as shown by slight wobbles in these asteroids' trajectories. This nearly doubles the number of such binary system asteroids that we are aware of. Gaia has been called a treasure trove, and it's hard to overstate just how much information can be found in these data releases. Gaia has provided us with the largest ever 3D map of quasars across the wider universe, identifying 1.3 million of them, with the earliest being spotted at the edges of the universe, with light that started traveling when the universe was only 1.5 billion years old. Gaia has found a previously unknown black hole in our Milky Way, 33 times the mass of the Sun and only 2,000 light years away from us. This type of black hole had never been seen in our galaxy before. Most local black holes are only 10 times the mass of the Sun, making this new find truly massive. Many more such discoveries can be found thanks to Gaia data. It's no surprise that ESA is already considering plans for a Gaia replacement, Gaia NIR, a space telescope similar to Gaia but able to see much further into the infrared to peer through the gas clouds that obscured Gaia's vision. But don't hold your breath for this one. If it goes ahead, Gaia NIR will look to launch in 2045 to provide an approximate gap between that mission and Gaia, to allow ESA to take even more advantage of parallax effects. Gaia NIR will be able to see how much further Gaia's observed stars have travelled in the intervening time. When it comes out, Data 5 will be the big one. Tentatively set to be released by the end of the decade, this data release will include everything, all 10.5 years of Gaia's mission, to the highest level of detail imaginable. It will truly be a treasure trove of information. Just think what discoveries can be made with so much raw data to sift through. Who knows what else we will learn about our galaxy. So, while Gaia's mission coming to a close is sad, the wealth of data it has collected is also very exciting. Our Milky Way galaxy might be surprisingly hard to learn about, but Gaia's data will give us the best crack at it to date. If you've loved the latest James Webb Space images, you need to see what I'm about to show you. ESA's Euclid Space Telescope has sent back its first batch of images, and they're some of the best space pictures I've ever seen. Known as Euclid's first light, this photo collection is a dazzling tour of the universe's galaxies, and scientists are freaking out at what they are seeing. Euclid's photos call into question our ideas of how the universe evolved, give new insight into the role of dark matter in structuring the cosmos, and even let us peer into the past by capturing galaxies 10 billion light years away. Plus, the photos themselves are just awesome, especially the last one. I'm Alex McColgan and you're watching Astrum. Join me today on a tour of what Euclid has captured so far, from glistening galaxies and swirling nebulae to star nurseries and even rogue planets. Let me show you why Euclid is such a unique telescope and how scientists plan to use its data to unlock the origins of the universe. On the 1st of July 2023, the European Space Agency launched the Euclid telescope from Cape Canaveral, Florida. After traveling about 1.5 million kilometers, it joined its siblings, the Gaia and James Webb telescopes, in orbit around the Lagrange point 2. This location is ideal for studying and imaging deep space. It allows telescopes to keep the Sun, Moon, and Earth behind them at all times so that they never interfere with observations. It's also close enough to Earth that communications are easy. Since L2 keeps pace with Earth's orbit around the Sun, we stay close to our instruments. Euclid's 6-year mission is designed to explore the composition and evolution of the universe. It will do this by building the largest and highest quality 3D map of the cosmos we've ever seen. In October 2024, Euclid started sending back the first pieces of this map, and I'll show them to you in a second. As Euclid continues to scan the sky over the next years, scientists hope the new data will help them understand the role of gravity and dark matter in the structure and expansion of our universe. First, you need to understand 3 things that make this telescope and its pictures so unique. Firstly, Euclid's ultra-wide lens captures more of the sky at once than any telescope ever has. It gathers high-resolution light data from billions of galaxies, some as far away as 10 billion light years away. Compared to ground-based surveys, it has 4 times the resolution and 15 times the sensitivity in the near-infrared. It can also spot objects hundreds of times fainter than the ones Gaia can detect. In a single observation, Euclid records vast cosmic structures and precise details of individual galaxies. The result? An image that conveys multiple cosmic scales at the same time, bringing home details in a way that makes researchers giddy. Secondly, Euclid measures subtle distortions in galaxy shapes caused by dark matter's gravitational influence, creating a gravitational lensing map. This is key to understanding how galaxy clusters grow and evolve, while also showing us how dark matter has played a role in literally shaping the universe. And finally, Euclid is creating a 3D map of the universe with 2 advanced instruments. The visible imaging system captures ultra-sharp images in visible light to measure galaxy shapes and positions, while the near-infrared spectrometer and photometer measures redshifts, placing galaxies in 3D space. In short, Euclid is kind of a big deal. The hype in the astronomical community around these images is real, as summed up by one Euclid project scientist. We have never seen astronomical images like this before, containing so much detail. They are even more beautiful and sharp than we could have hoped for, showing us many previously unseen features in well-known areas of the nearby universe. So let me take you on a tour through Euclid's first light images one by one, starting with our map. Thanks to ESA's Gaia and Planck missions, we already have a pretty solid map of our Milky Way. Euclid is tasked with gathering data on the dark parts of the map. So far, it has covered about 1% of the map it was sent to create. Between the 25th of March and the 8th of April 2024, Euclid took 260 pictures of the southern sky, covering an area 500 times the size of the full moon we see from Earth. Putting these images together, scientists created a mosaic spanning millions of stars and galaxies. And remember, this is just 1% of what it's planning to do. Because Euclid captures both big picture and detailed data at the same time, researchers can see the sky at different scales. From extragalactic views, we can zoom into the galaxy clusters, their core, and even individual galaxies. So, let's explore some of these cosmic structures, starting with one of the biggest known in the universe. This is the Perseus cluster, located 240 million light years from Earth. This image shows over 1,000 Perseus cluster galaxies and more than 100,000 faraway galaxies in the background. Scientists think the way galaxies are organized can tell us a lot about the distribution of dark matter and dark energy. You see, gravity might cause dark matter to organize itself into filaments. We aren't sure, but NASA scientists believe it's possible that where these filaments intersect, galaxies stick closer together, forming a cluster. The theory goes that if there were no dark matter, galaxies would be distributed evenly throughout the universe, which obviously isn't the case. While many galaxies in the Perseus cluster are already known, cosmological simulations predict there should be several dwarf galaxies there too. If we could see those faint galaxies, we could analyze their shape and distortion relative to the cluster and background to determine how dark matter is distributed. The problem is, these dwarf galaxies tend to be overshadowed by older stars shining infrared light, so they've evaded direct observation. Until now. Euclid discovered more than 630 previously unknown dwarf galaxies, which is a huge breakthrough in the study of dark matter. More than dark matter, Euclid is also teaching us about star formation too. Let's go to our next destination and I'll show you. Say hello to irregular galaxy NGC 6822, shining bright 1.6 million light years away. It was first identified as a remote stellar system by Edwin Hubble in 1925. Now, almost 100 years later, Euclid is sending back high-resolution images of the entire galaxy and its surroundings. The James Webb Space Telescope did also image this galaxy a few years ago, but a much narrower field of view. Scientists are interested in Euclid's wide-angle photos of this galaxy for what they might tell us about star formation and the early universe. You see, stars smash lighter atoms like hydrogen and helium together to produce heavier atoms, including metals. This process happens across a star's lifespan, and is why we don't see many heavier elements in the early universe, because they take time to accumulate. Surprisingly, many of the stars in NGC 6822 have very low levels of metal atoms. By studying low metallicity galaxies like this one, scientists hope to learn more about how galaxies evolved in the early universe. Euclid has made that a monumentally easier task thanks to the color information from its NISP instrument and its wide field of view. Euclid has also revealed several previously unknown globular star clusters and H2 regions in this galaxy. H2 regions are the colorful gas clouds we see here. When stars are born, they emit light so strong and bright that it ionizes the hydrogen gas surrounding them, resulting in these H2 regions. Studying these will help us better understand the cloud properties at the time a star is born, and what conditions are needed for massive star formation. Speaking of globular clusters, here's one in a different part of the sky. Globular cluster NGC 6397 is 7,800 light years from home, making it the second closest one to us. This image is one part of a wider image from Euclid, which I'll show you in a little bit. Globular clusters are kind of like Hollywood, a high concentration of stars in one place, where everyone is trying to outshine everyone else. What does this mean? The smaller, dimmer stars get drowned out by the bigger, brighter ones. On top of that, they extend quite a long way out from their center, with the radial parts mainly made up of low-mass, faint stars that, until now, have been hard to see. Ironically, it is these faint stars that hold the most scientific interest for unlocking the history of the Milky Way. As David Massadri of the National Institute for Astrophysics in Italy puts it, currently no other telescope than Euclid can observe the entire globular cluster and at the same time distinguish its faint stellar members in the outer regions from other cosmic sources. Hubble actually imaged the center of this cluster in 2021, but to image the entire cluster, including the sprawling outskirts like Euclid did, would have taken it far too much time and resources. On the other hand, Euclid snapped this shot in just 1 hour, and it is absolutely beautiful, both aesthetically and scientifically. Sometimes we see stars arranged like this, and sometimes we see them arranged as spiral galaxies. Yet, despite living in one, we don't actually know how they maintain their shape. The next Euclid pictures aim to help answer those questions. Caldwell 5, also known as the Hidden Galaxy, is hard to observe because it lies in the busy disk of our Milky Way, about 11 million light-years away. It tends to get overshadowed by dust, gas, and other stars. It is considered a look-alike galaxy to our own, which makes it a prime point of interest for researchers. It's pretty hard to study a galaxy you're inside of, since you only get to observe it from one plane. Euclid's near-infrared instrument was able to pierce through the dust and reveal the galaxy in all its glory. We've captured it before from the ground, but with nowhere near the detail Euclid manages. The Euclid image might look normal, as if every telescope can make such an image, but that is not true. What's so special here is that we have a wide view covering the entire galaxy, but we can also zoom in to distinguish individual stars and star clusters. We can trace the history of star formation and better understand how stars formed and evolved over the lifetime of the galaxy, says Euclid Consortium scientist Leslie Hunt. We still don't fully understand how spiral galaxies maintain their structure, or the role dark matter plays in forming them. Euclid's ability to capture this galaxy's sprawling spiral arms and dust lanes in such detail will help scientists understand the link between dust, gas, and star formation on a large scale in a way we've never been able to before. Sadly, we've only got one more stop on this cosmic tour, but I've saved you the best for last. Let's see what these colourful clouds are hiding. Our fifth and final photo shows the Horsehead Nebula. It has been photographed by various telescopes before, but never with such a sharp and wide view as Euclid managed. Again, this shot was taken in just 1 hour, which is absolutely mind-blowing. It's like someone just stopped at a viewpoint and snapped the picture. Located approximately 1,375 light-years away, this is the nearest massive star-forming region. It lies just south of Alnitak, the easternmost star in Orion's 3-star belt, and is part of the expansive Orion molecular cloud. It is in this swirling nebula that scientists hope to find evidence of many previously unknown Jupiter mass planets. One such planet has already been identified, Sori 62, a young planet 10 times the mass of Jupiter and a temperature of 1,200 degrees Celsius. The clouds behind the Horsehead Nebula are illuminated by UV radiation from nearby star Sigma Orionis, while the clouds of the Horsehead Nebula itself are made up of cold molecular hydrogen, which gives off barely any heat or light. This makes the Horsehead Nebula an interesting place to learn more about star formation, as scientists can observe and compare how stars form in dark, versus bright clouds. Sigma Orionis is part of a group of stars called an open cluster, which researchers hope to get a more complete picture of with Euclid's data. For example, free-floating planets have been known to exist in Sigma Orionis, but with Euclid's ultra-high sensitivity, scientists found many smaller FFPs than were previously documented. As one research paper put it, FFPs in that zone appeared to be ubiquitous and numerous. And this is just the beginning. With another 5.5 years of mission time left, Euclid still has a lot of ground to cover. Along the way, the data and images it collects will be pivotal to helping scientists unravel the mysteries of dark matter, dark energy, and the origins of stars, galaxies, and the universe itself. A 3D map of the distribution of dark matter could be revolutionary to our understanding of fundamental physics. Until then, we'll just have to entertain ourselves with more images as they come out. Thanks for watching. If you like this video, you may like my other videos on space tech and innovation. Did you hear about JAXA's precision landing on the moon? It has the potential to catapult us into a new era of planetary exploration, but it didn't totally go according to plan. Click here to watch it now, and I will see you next time. Thanks for watching. I really want to give a huge thank you to our astronauts on Patreon. It's really becoming a thriving community, and I've loved reading all your messages and comments over there. If you'd like to join in, then you can visit the link in the description to become an astronaut and bring the channel more stability than the algorithm. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.